Ah, that feeling. We've all had it. You're staring at thousands of lines of, old code. Maybe it's yours, maybe it's from someone who left the company years ago, and you're just thinking, nope, I am not touching that manually.
Mm-hmm.
And that's when the hero of modern development arise, right? Yeah. The automated linter, the tool that promises to not just find the messes, but to clean them up for you.
It's the ultimate siren song of efficiency, isn't it?
Yeah.
We all want that button that just makes the technical debt disappear.
Exactly. And today we're doing a deep dive into one of the fastest linters in the Python world, Ruff check.
And specifically, we're looking at its most powerful and potentially its most dangerous feature, the ability to apply fixes automatically, that little fix flag.
Our source material for this comes from a blog entry by Ang, who calls themselves an old software plumber, and they laid out this really meticulous workflow, with the best intentions.
Right.
But despite all that, their automated cleaning process just silently shattered their code. They had what they thought was the perfect setup, and yet it broke.
And that's our mission today, to really dissect that breakage. We need to understand the critical and often tiny configuration safeguard that separates a tool like Ruff from being, well, a ticking time bomb.
Especially with legacy projects.
Especially. You might think your configuration is fine, but as we're about to see, one single line can undermine everything.
Okay, so let's set the scene for this. This software plumbing disaster. The author was really focused on continuous code hygiene, which, is admirable.
Absolutely. They integrated Ruff check right into their version control system using pre-commit hooks.
Which, for anyone listening who might not be familiar, pre-commit hooks basically make sure a bunch of quality checks run before you can even commit your code to the repository.
It's standard best practice. They were being smart. They were forcing code quality at the source. And their setup wasn't casual at all. It included some very specific defensive arguments.
They used fix to auto-apply changes.
Right.
And crucially, they also used exit non-zero on fix.
And that second argument, that's supposed to be the safety net.
Right. The idea is if Ruff applies a change, the hook fails the commit. It forces the developer to see the change, approve it, and then commit the corrected code in a second step. The human is supposed to stay in the loop.
Exactly. The author thought they had minimized the risk by forcing that manual sign-off on the fact that, a modification happened. But here's the genuine surprise. This is the core lesson. Despite this careful setup, their entire test suite broke immediately after Ruff applied its changes.
Okay, but hold on a minute. If they used fix and the commit failed because changes were applied, didn't that give them a chance to review the fix? Why didn't that process catch the breakage?
That is such a critical distinction, and it's something you really have to be aware of. The commit failed because the files were modified.
Okay.
So the developer reviewed the changes Ruff made and saw what looked like a perfectly clean, modern Python change. Ruff itself didn't crash. It didn't complain. It just applied the fix successfully and internally validated that the new code was structurally sound.
I see the trap now. So the pre-commit hook only checks if Ruff ran successfully and if it made changes. It doesn't check if those changes will, actually run in the project's real-world environment.
Precisely. The code was cleaned up. It looked syntactically fine, but it was completely non-functional in their target environment. The failure didn't happen in pre-commit. It happened right after, when the test suite kicked off.
The test suite that was actually built to respect the project's real version requirements.
Exactly. And the investigation didn't lead them down some complex rabbit hole of dependencies. It led them to a single source of truth for the linter, the project's main configuration file, pyproject.toml.
It's just fascinating how one sort of innocent-looking setting can dictate the entire behavior of a modern tool and push it way beyond what a project can actually handle.
And that setting was the target version. In the tool.ruff section of that config file, the author had set target version Py3.14.
Python 3.14. Wow. For anyone listening, that is either highly aspirational or maybe it's real, depending on when you're listening to this. It's definitely not the baseline for legacy support.
Right. It signals to Ruff, hey, treat this code like it's running in a super modern, cutting-edge environment. The author might have set this to future-proof things, or maybe it was just a typo. Who knows?
But the result was the same.
The result was the same. They basically gave the linter permission to be as aggressive as possible in its modernization efforts.
And here's where it gets really interesting. By setting that target version so high, they accidentally turned on a specific category of rules in Ruff that are, They're inherently risky for backwards compatibility.
That's right. Ruff rules are categorized, and the ones about modernizing code start with UP for Pi upgrade. And these UP rules are, by their very nature, aggressive. Their entire goal is to get your code from old patterns to new ones.
And unlike basic style rules, like E for error or F for flaky code,
Right, those are different. The UP rules often introduce features that simply did not exist in older Python interpreters.
and the specific rule that caused all this trouble was UP017. So what does the datetime time zone UP017 actually make Ruff do?
Its purpose is actually excellent. It's rooted in Python best practices. UP017, it aims to modernize datetime usage. In older Python, if you wanted a time zone-aware timestamp for UTC, you had to import the time zone class and then reference timezone.utc. It was a bit verbose.
A bit clunky.
Yeah, and the Python standard library recognized this and created a cleaner constant.
And Ruff, being the diligent tool it is, just went ahead and applied that cleaner constant. Let's look at the exact change the author pointed out.
Okay, so before the fix, the working code had this line from datetime time zone, and then the usage would be something like datetime.now timezone.utc.strf time. This was perfectly functional in Python 3.0, which the project required.
But Ruff, reading that Pi 3.14 target, just stepped in and optimized it.
The change was swift. Ruff modified the import from datetime import UTC datetime.
Okay.
And then the usage line changed to the much cleaner, much shorter datetime.nowutc.strf time.
Which is beautiful, modern Python.
It is. It's cleaner. But this is the crucial moment of failure.
So why did this seemingly simple name swap just instantly break their entire test suite?
This is the absolute version constraint clash. While datetime.utc is a wonderful change, it was only officially introduced into the standard library in Python 3.11.
Huh.
And because the author's project needed to support older Python versions specifically, they had to run on Python 3.1. The moment that automated fix was committed, the 3.1 test runner saw this new UTC constant and had no idea what it was.
It just failed. An instant dependency error.
A fundamental name lookup error. Yep.
Wow. So the tool was perfectly successful at its job, modernizing the code according to the configuration you gave it, but it was successful in a totally wrong context.
Exactly. It followed the context in the config file, the Pi 3.14, not the constraint required by the environment it was actually running in, the 3.10.
It's a perfect example of configuration misalignment being, well, fatal. The developer manually said, treat this like the future. But the project dependencies were screaming, we must function in the present.
And this really highlights the critical difference between those two failure states. The pre-commit hook failure only told you that Ruff had done work.
Right.
The later catastrophic test suite failure confirmed that the work it did was incompatible. The lesson is so clear. Automation just doesn't replace environmental awareness.
Okay, so let's unpack this and talk about the defensive mechanisms. If you listening right now are responsible for bringing a powerful tool like refcheck into a legacy project or anything with tight version constraints, what are the key takeaways for preventing this kind of silent sabotage?
Well, the first big one is to adopt a review-first strategy, especially when you're first integrating it or doing a mass cleanup. The author's initial impulse was to go straight to fix.
Which is what we all want to do.
Of course. But that level of trust is just too high when these modernization rules are involved.
So you need to slow the process down, especially if you're dealing with thousands of files. What should they have used instead of fix?
The recommended command for that initial review is ruff check diff.
Okay, diff.
Yeah. This command runs the linter. It finds all the recommended changes, including those aggressive UP rules like UP01 halvin, but instead of just applying them, it generates a giant human-readable patch. A diff.
That's a fundamentally different approach. It turns Ruff from a mechanic who fixes the car while you're not looking into an inspector who hands you a detailed report of all the proposed repairs.
Precisely. If they had run diff at the beginning, they would have seen hundreds of lines of changes, and a big chunk of them would have been that timezone.utc to UTC replacement.
And seeing that across 50 files would immediately raise a human flag.
It should. You'd think, wait a second, is this UTC constant even available in Python 3.0? And that whole review process happens before a single file is actually changed.
Okay, so that handles the risk of a big automated breakage. You trade a bit of time for a massive increase in safety, but what about the permanent fix? Because you don't want the linter constantly suggesting features you can't use.
That is the pinning solution, and it is the single most critical configuration step. If you support multiple Python versions or any version that isn't the absolute latest, you must ensure that the target version in your pyproject.toml DOM reflects the oldest version of Python your project supports.
So the single source of truth for your linter has to be the constraint of your runtime. If you support 3.cm, you pin to 3.cm.
Absolutely. The configuration has to reflect the floor of your compatibility, not the ceiling of your aspirations. If your project has to run on 3.10, telling Ruff it can use 3.14 features is just. You're explicitly inviting this kind of breakage.
So the author didn't just walk away with a painful lesson. They actually fixed it with concrete config updates that we can all learn from. So how did they lock it down?
First, the crucial change. They corrected the misconfiguration in pyproject.toml. They changed that one destructive line from the aspirational target version equal py314 to the version the project actually needed. Target version py310.
And that single change automatically turns off all the rules that require a newer Python version.
Immediately. It prevents the UP018 rule from even suggesting the illegal datetime.utc constant.
That's the structural fix.
Yeah.
But they also updated their day-to-day workflow, right? Moving away from relying on autofit.
Yes, they updated their pre-commit hooks, too. They switched the configuration for the Ruff check hook away from those aggressive arguments, away from fix and exit non-zero on fix, and they replaced them with just the diff argument.
So they made a conscious operational choice to shift from Ruff fixes it, then I confirm a change happened, to Ruff suggests changes, I review if the suggestions are safe, and then I apply them myself.
It signals a really fundamental and mature understanding of automation risk. They recognize that for modernization rules, velocity has to take a backseat to stability and compatibility. For simple formatting, sure, let the tool fix it. But when you're changing fundamental language usage, those UP rules, human review of the diff is essential.
This has some pretty profound implications, and not just for Python. So what does this all mean for you, the listener, whether you're working in Python, JavaScript, or Rust? The core insight here is that automation is a force multiplier. It will make you faster, sure, but it will also amplify your mistakes if its scope isn't strictly constrained by the reality of your production environment.
Exactly. The power of these tools is their deep knowledge of how a language evolves. If you tell the tool you're on the cutting edge, it's going to apply the latest, cleanest patterns. But if your actual environment is older, that tool instantly stops being a helper. It becomes a breaking change delivery system.
A single line in a configuration file target version was the difference between this tool being an aid or an absolute nightmare. Always make sure the tool's assumptions align perfectly with the constraints of your system. If the environment needs 3-point hen, you tell the linter 3-point hen. Don't give it aspirational instructions.
And if we connect this to the bigger picture, this whole story is about guarding the boundary between modernization and stability. When you introduce automation, you have to explicitly define that boundary. If you don't, the automation will define it for you, and that can lead to some really painful production-level runtime failures that you just never saw coming during your clean commit process.
It's a fantastic lesson in configuration management and the risk that comes with upgrade automation. And to leave you with a final provocative thought. The author of this post, Ang, isn't just a Python developer. They write about everything, free and open source software, Elixir, Haskell, Rust. So given how critical pinning the target version is for Python linting to manage this risk, what analogous explicit constraints should you immediately check when you integrate new aggressive automation tools in those other ecosystems? Think about a formatter in Elixir or a static analyzer in Rust. What's the equivalent of target version there that could save you from a similar kind of silent dependency breakage? Think about that the next time you're about to hit the fix button in a new environment.